Hello and welcome everyone. Today inshallah we will continue on the inverse function NRN, and then I will go through some of the implicit functions, the beginning of the as an introduction with the inverse function. It's really very important. I know today is second day of Ramadan, and I know it's hard just to go through everything, but we will try to do our best just to go through it as smooth as possible. And you have everything, as you know, it is already found on Moodle. So all the data, the recorded lectures from Lisbon is already there on Moodle, and also you will find these recorded lectures on the YouTube. So you should be in a very good, shape. Today, as I told you, we will continue on the inverse function. There is some part in it that we couldn't finish in the previous week. We had the introduction with R, but today I'm going to go with you with Rn. It's exactly almost the same methodology and same everything with the theory of inversion, but with slight differences. So let f belongs is such that the domain belongs to Rn, into Rn, be class C1 function, and we already defined C1 functions in the previous lecture, that any C1 function is continuous, it is differentiable within the first derivative, such that the determinant of the Jacobian of f doesn't equal to 0, and this is relative to the derivative of the function doesn't equal to 0, in order to be able to use the inverse theory as we did in the previous lecture. So this guy here is the corresponding part for having the first derivative doesn't equal to 0 in the neighborhood of the point that you will do the inversion on it. For all x belongs to d, then f is invertible. The inverse function g is going to equal to f minus 1 is also plus 1. So as f is class 1, so its inverse also will be class 1. And j dash, which means the inverse, the derivative of the inverse of an f of x, will equal to 1 over f dash x. This is something I want you in all times to be careful about, that we have g dash of f of x. So these are the y values, which equal to 1 over f dash of x. This is the x values corresponding to these y values, either if you have just only one variable, so a function in one variable, or a function in several variables, it will be the same. So those guys are the y, or the values of the function, and those are the corresponding input values, but with the derivative of f dash x. This interpretation of this theory shows you or identify that the derivative of the main function shouldn't equal to 0 in order to get the inversion as I told you. In Rn, I've written all of this. For functions in Rn, the equivalent to the derivative is non-zero if that the determinant of the Jacobian is non-zero. And that's what I told you about. The determinant of the Jacobian of f doesn't equal to 0. So it's exactly the same. So once more, in Rn, the equivalence to the derivative is non-zero, that this guy doesn't equal to 0, and that determinant of the Jacobian is not equal to 0. In that and enough condition for the function of class C1 to be invertible, if this enough for a function to be invertible in Rn, unfortunately the answer, it is not enough. The answer, it is not enough. Why we say that? Because sometimes we may have cases that the determinant of the Jacobians are not 0 and the function are not invertible. So we had a couple of cases, where although the function by itself or the determinant of the gradient of the function doesn't equal to 0, and still we can't get the inverse of this function, or it's not invertible. Sometimes it's locally or globally invertible. So Some cases you will have that the determinant of the Jacobian doesn't equal to 0 and the function is invertible. We may say something like this. And also sometimes the Jacobian doesn't equal to 0 and still the function is not invertible, or even though the Jacobians, I will go through just something like this, and in some cases we may have the Jacobians itself equal to 0, but we can get the inverse. So there is special cases after. So the determinant of the Jacobian doesn't equal to 0. It's a sufficient condition, but not a necessary one for f to be locally invertible in a neighborhood of certain point. In order to show this, I will give you a couple of examples. Some examples that will show you how to be sure that we can get the inversion of this function. Of course, it needs a huge background, okay? It needs you to understand these examples very well, and please, I would like you to resolve these problems within your hand as usual. It will make a huge difference. So, let's go through the first one. It's an example on the function determinant is not 0, so you will see here that the function, the Jacobian determinant doesn't equal to 0, okay? And the function is invertible from R2 into R2. So this is the case that you will find that your function, everything is smoothly and is correct. The Jacobian doesn't equal to 0 and it is inverted, which represents the linear transformation of a linear function. So if I have y1, y2 equal a11 x1, a12 x12, and this linear transform moves the stuff from R2 into R2. I will give you a very nice example on this. So it can be written on this form. These are the y values, and this is the transformation matrix, and these are the inputs x1 and x2, which can be easily written as y equal the transformation matrix, which is A times X. So for example, if I have 2x1 minus 3x2, 1x1 plus 1x2, this is then for y1 and y2. So this matrix or this transformation can be put on simply on this matrix form. I can put it simply on this matrix form. So I have the plan of R2, which is y1, y2, that will make a transform in the values of x1, x2 in the following manner. It's a 2, -3, 1, and 1. So what's happening here is I have R2 into R2 using the transformation matrix, which is 2, -3, 1, and 1. If you want to see how this transform works, it's really very simple. All I have to do is just to see for this is the y-axis and that is the x-axis. I will choose point 1 and 0, and I will choose also the point 0 and 1. These 2 points are really very good examples, because once you connect 0, 0 and 1 and 0, it will give you the positive direction of the x-axis. So it's a point on the x-axis within positive direction. The point 0 and 1, it's a point on the positive direction of the y, and it determines the direction of the positive part. So if I want to show you how this linear transform works, all I have to do is to get the corresponding values for y1, y2, and this is for the first point, which is 2, -3, 1 and 1. Let's see if I put in this transform 1 and 0. So actually, I will see how this point is moved. So once you do so and you multiply by 1 and 0, you will keep the first column. So 1 and 0, it will be represented in 2 and 1. So instead of working with this point, which is 1 and 0, I will go for 2 and 1. So this is for 2, for example, and that's for a 1, and this is the new point. So if this B1, this is gonna be B1 dash. And so the new direction of the x-axis, the new x-axis, is this one, which moves from 0 to the point which is 2 and 1, as you can see. If I want to see the new y-axis, it's going to be really very simple. All I have to do is just to make the substitution of 0, 1 instead of 1, 0. So you will have y1, y2, and now I'm trying to get, this is b1 dash, I'm trying to get b2 dash. So all I have to do is to use these numbers, 2, 1, negative 3 and 1, times 0 and 1. Once you do so, you will have the second column. So the second column is going to be negative 3 and 1. So instead of representing 0 and 1, this point will be moved to negative 3 and 1. So I will go here, this is negative, let's say negative 1, negative 2, and this is negative 3. So this is the point, the x value or the new y value. And the other point is a 1, so it's coming like that. And connecting these two together, it will give you the new y-axis. So this is the new positive direction for the x-axis after transformation, and this is y after the transformation. So now, with the use of this linear transform, I can rotate the x and y and move them to the points 2 and 1 and negative 3 and 1, as you can see. The question is, if this transformation, or if this linear transform is reversible, so I can move stuff, as you can see, 1 and 0, 0 and 1, from the x1, x2 plan into y1, y2 plan. Can I do the vice versa? Can I move stuff from y1, y2 into x1 and x2? Okay, we will see. So now I have them. This is exactly what we did. This is the first point, 1 and 0, with more elegant way instead of this graph. And this is 0 and 1. So this is on the x-axis, that's on the y-axis. So once you start substituting, as I told you, from R2 into R2 using this transformation, 1, 0, 0, and 1, the new points will be 2 and 1, negative 3 and 1. And this is actually the x-axis positive direction and the y-axis positive direction. Now, if you try to get the determinant of this linear transform, as I told you, this transformation is invertible. If a determinant is not 0, that's the Jacobian is not 0. So I'm going to get the determinant of this transformation matrix, which is going to equal to 5, not equal to 0. So I can, instead of having y equal ax, I can get the inverse, x equal a minus y. And if you remember, forgetting the inverse of this matrix, it's gonna be an easy job to get. So all I have to do, it's a 2 by 2 matrix. So I'm gonna make it like 1, 2, and this is 3 and the negative 1. And for all the elements, this is the adjoint matrix. All I have to do is just to divide on the value of the determinant, which is 5. As you can see, this is 2 plus 3. So the inverse gonna be 1 over 5 minus 1 over 5, 3 over 5, 2 over 5. So now I can get x1, x2 depend on the inverse matrix times y1 and y2. So multiplying by the inverse matrix, it will make this guy disappear, this matrix, and will leave me with x1, x2 will gonna equal to 1 over 5, 3 over 5, negative 1 over 5, 2 over 5, and in this manner, if I start to move stuff from vice versa, I can. So let's give it a try. If I put here 2 and 1, so 2 and 1 and start substituting. Once you start multiplying, so it's gonna be 1 over 5, and this is gonna be, 2 and 1, so it's gonna be 2 over 5, but 3 over 5, which is gonna be, the result is 1, which is this guy. And if I try to multiply the second row by, as I told you, 2 and 1, it will be negative 2 over 5 plus 2 over 5. The sum is going to be 0. So exactly, if I put these values instead of y1 and y2, I will get 1 and 0. So now I can move from y into x and vice versa. This is the power that we will have using the inverse function. This is why it's really very important. Okay, you have another example which gonna express also the meaning that we are talking about. So within this one, we saw that the Jacobian doesn't equal to 0. Everything is smooth, it's invertible, everything is very nice. For this example, this mapping maps R2 into R2. So from xy, it will be mapped into 1 over x squared and x squared y plus 1. So I'm mapping from r squared into r squared. First of all, these functions are C1 functions. So this function satisfies the differentiability and continuity of the derivative through the domain, except at 0. C, this is a rational function, so it is continuous in differentiation. And the one beside it, it's a polynomial function, so also it's defined in continuous differentiation, which means that it's a C1. It's actually a C goes up to infinity, so of course it's going to be a C1 function. So the first condition is satisfied for the domain, with the domain. Of course, the domain of this transform of this function, it excludes 0 because of the first component. So through the domain which the function is defined, everything is perfect and it is C1. Now the function and its partial derivatives are differentiable of class C infinity, so it satisfies C1 as I told you. This is a rational function and this is a polynomial function. Let's get the Jacobian. The Jacobian of these functions, because you are talking about functions in R2, and you have two functions, please do review all the previous chapters. It's all working together. So I can't just go through invertibility without knowing how to get the Jacobians, how to be familiar with, how to be comfortable moving around them. So all I have to do now is to get the Jacobian of f. So the Jacobian of f, it's gonna be the partial f partial x, this is f1, partial f1 partial y, and this is partial f2 partial x, partial f2 partial y. So all I have to do is simply start differentiating as I told you. So I would start with from R2 to R2. F1 stands for the first function, which is 1 over x squared. So I will differentiate with respect to x, so it's going to be negative 2 over x cubed. Then I will differentiate this guy with respect to y, and there is no y's here, so it's going to be 0. So it's going to be, for this one, it's going to be negative 2 over x cubed, but this guy is going to equal to 0. If I went for f2, which is x squared y plus y, so differentiating with respect to x will leave you with 2 over xy. But differentiating with respect to y for f2, once more this is f2, it's going to leave you with x squared plus 1. Okay? Once more, as I told you, this is the determinant of the Jacobian. It's going to be the derivative negative 2 over x cubed. But this guy doesn't contain y, so differentiating with respect to y is going to be 0. For the second f, which is x squared y plus y, differentiating with respect to x will leave you 2xy, with respect to y is going to be x squared plus 1, as you can see. Now I have the derivative, I have the Jacobian. And I can get the determinant of this Jacobian, which is very, very simple. Multiplying the elements of the principal diagonal minus the elements of the secondary diagonal. So you will end up having negative 2x squared plus 1 divided by x cubed. Of course, this value doesn't hit 0. How it's gonna hit 0? How it's gonna hit 0? 0 will be developed from a denominator. And the denominator here is 2 times x squared plus 1. if you remark that the denominator will never be 0, I don't care about the denominator because I excluded already 0 from the denominator, okay? So this is not gonna be 0 for every x and y. So now the two conditions for the time being are satisfied. Two conditions are satisfied. The Jacobian determinant is never 0, and it is globally invertible in R1. In R1, it's gonna be okay. That's a sufficient one because the derivative doesn't equal to 0. But in R2, it's not gonna be sufficient. If you remark for the 2 points, 1, 0, negative 1 and 0, just these 2 points. If I tried to make the substitution here in 1 and 0, okay, and 0 and 1, as I told you, so let's try to go through this. Okay, so f at 1 and 0, it's going to be 1 and 0. And also f at negative 1 and 0, it's going to be the same. It's going to develop 1 and 0. So unfortunately, although the derivative is satisfied, derivative of Jacobian doesn't equal 0, and it's a C1 function, so both two conditions are really okay. But if you try to use these numbers, unfortunately, it's not going to be an injective, a one-to-one function. So once more, if I try to get f at 1 and 0, let's do the substitution. It's going to be 1 over 1 to the power of 2, which is going to be a 1, and x squared times y. X squared is 1 times y, which is going to be 0, plus 0, so it's a 0. Same way, at f equal to negative 1 and 0, it will develop 1 and 0, exactly in a similar manner. So this is not a one-to-one function, so it cannot be globally invertible. But it can locally be invertible in the neighborhood of just only one of these points. But generally, it's not invertible. And this is what's written here. So it cannot be globally invertible, but it is locally invertible around each point in its domain. So some points, although it's not globally invertible, but it may be invertible within some restrictions. Okay, that's another example, also really very important example, which hack the part that you have polynomials, and as you will see right now, it is C1, of course it's C1, and also if you tried to get the Jacobian, let's discover what's gonna happen. So what I'm going to do at the time being, we will have to check the two conditions. That the function is C1, and then I will get the determinant of this, the determinant of the Jacobian of this function in the neighborhood of the origin as it is requested in this example. So the first thing to remark that these two guys are polynomials. It's from R2 into R2, but these two guys are polynomials. So it's gonna go forever. So it's a C infinity class, so it's a C1, so the first condition is satisfied. Now let's discover the Jacobian. If I try to get the Jacobian, I will try to get partial f1 partial x, partial f1 partial y, same way like partial f2 partial x, partial f2 partial y. So this is gonna be the Jacobian, as I told you exactly, partial f1 partial x, partial f1 partial y. This is for f2, exactly the same. Now I'll start differentiating. If you remark, if I want to differentiate this function, it's gonna be really a piece of cake, because we are going to make our partial derivatives. So the determinant of the Jacobian at f, and I will start differentiating. For the first function, which is x plus y to the power of 3, once you try to make the differentiation, it's gonna be 3 of an x plus a y to the power of 2. This is the derivative for x. Now going to the derivative of y, which is gonna be almost the same. Okay, the power will go down, so it's going to be 3 of x plus y to the power of 2, exactly the same. Once more, if I went to x minus y to the power of 3, and this is for f2, and start, as I told you, to get the partial derivatives with respect to x and with respect to y. With respect to x is going to be 3 of an x plus an y squared. And of course times 1 because derivative of x is equal to 1. But for the other guy, which is x minus y to the power of 3, it's going to develop, the powers go down, x minus y to the power of 2 times the derivative of negative 1, which is going to be negative 1. So this is the result that we are talking about. If I make a substitution at the origin, you will end up having GF at 0 and 0, which is going to be simply 0 plus 0, which is 0, 0, 0, and 0. And of course, the determinant is going to be 0. So now, from a look to this problem, this condition is not satisfied. So, if we are in R1, it's not going to be invertible. But here in R2, although that the determinant at 0 and 0 is equal to 0, so this function shouldn't be invertible. But since the conditions are not met, so the function is not invertible. But the inverse of the function is possible here. I will show you how to do it. I can get the inverse of this function. It's a polynomials, there is no problem with them. See, let's go for this case. I will let these two values to be a u, which is equal to x plus y to the power of 3, and the v, which is x minus y to the power of 3. I will make these two guys in this manner, which is going to lead to that x plus a y is going to equal to the cubic root of u, and the x minus y is going to be the cubic root of v. Now I can solve this system of equations together in order to get the values of x and y as functions in u and v. Simply add these two guys together. So you will end up, if you add them together, you will end up having a 2 of x equal to the cubic root of u plus the cubic root of v, which means that x equal to cubic root of u plus a cubic root of v divided by 2, and that's the x component. If you make a subtraction, subtracting the first function from the second one, you will end up having y equal to a cubic root of u minus cubic root of v divided by 2, which means it is invertible. Now you have x and y as functions. As you can see, I brought cubic root for both sides, so it's a cubic root for u, it's a cubic root for v. Now adding and subtracting, I will get 2x and 2y. Now I have x and y as functions in u and v, so I have inverted my transform. Bottom line, that it is sufficient condition for the Jacobian, but not a necessary one. By hitting this relation, and this is the slide of the solution altogether, and of course this condition is not satisfied. Although it's not satisfied, so according to the theory, if we talk the theory with all the details as it is, you will discover that although the determinant equal to 0, but still we could get the inverse. So from a point of view, this function or this theory in Rn, it is sufficient, but not a necessary condition to exist. These couple of questions from quizzes is going to be similar to what you can see in exams or something. It's very, very simple, but it needs you to have a good understanding of what we are doing and to go through them step by step as I told you. Here he's telling you that g such that from R2 into R2 be the function with expression 2mxy and x squared plus y squared. So it's a function g, which is 2xy, x squared, y squared. So I will write it down for you. So this is the g that I'm telling you about. It's a function in x and y, so from R2 into R2, and this is the function that we are talking about. the function goes like this. The first component is a 2x and y, and this is x squared plus y squared. And the alternatives is g is not invertible, since the Jacobian determinant of g evaluated at some points is 0. So once more, is asking you or telling you that it's not invertible since the Jacobian. G is not inversible, so it is not one-to-one. And this is something we need to think about. G is invertible since G is a class C1 function. A class C1 function is one of the conditions, but it's not sufficient and necessary to have it invertible, so I will exclude the last result. In anyhow, we need to get the Jacobian of this transform. So the Jacobian matrix of this transform gonna be differentiating the first function with respect to x. That leaves you to y. Then differentiating with respect to y, that will develop a 2 over x. Then I will go to f2, differentiating with respect to x, which is gonna be a 2 of x. And for the second part, differentiating with respect to y, so it's gonna be a 2y. If you wanna get the determinant of the Jacobian of f of g or f or whatever, this function, so it's gonna be a 4 in y squared minus a 4 in x squared. So this is the Jacobian. So g is not invertible since the Jacobian determinant of g evaluated at some points is 0. You are not sure about this because actually it's not going to be invertible at these points, but maybe invertible at other points, and it's a C1 class. G is not invertible since it is not one-to-one, and let's discuss or think about this value. Let's use the two major values that we usually like. Let's try 1, 0 and the negative 1 and 0 and see. If I inserted in this function g, so I will get g of 1 and 0. It's just making the substitution. 2 times 1 times 0, which is going to be a 0. And 1 squared, so it's going to be a 1. This is the first value. For g at negative 1 and 0, let's see. Negative 1 times 2, negative 2 times 0, so still a 0. And for negative 1 and 0, it's going to also be 1. So this function includes or indicates that at two certain different points in the input, the output is the same point. So it's not a one-to-one function, and this is major, so it's not invertible. So the correct answer will be g is not invertible since it's not one-to-one function, and you have here your reason. Okay, for this one, let g r squared into r squared, so it's a function running from r squared into r squared, and I believe he gave you 2xy, x squared, y squared, same. Regarding function g, we can state that g is not locally invertible in the neighborhood of 2 and 0, so it's not locally invertible in the neighborhood of 2 and 0. Let's make a substitution. So if I make a substitution at 2 and 0, so it's gonna be like this: 0, 4, okay, and also 4 and 0. And this is the determinant of this function. So getting the determinant of the Jacobian, so this is the determinant of Jacobian at g, which is going to equal to negative 16. It means it's not equal to 0, and it's C1 function. So the first is alternative. It is not, and take care about the not here. Okay? It's not locally invertible. This is not true. It is locally invertible in the neighborhood of 2 and 0. I share for this guy, this is correct. The theorem of the inverse function shows that g is locally invertible in the neighborhood of 0 and 0. If you try to make 0 and 0, it's going to be equal to 0, and the theorem doesn't state that. So this is not correct. Once more, if you make the substitution here at the origin, all of this will be zeros, and the determinant will be 0. The theorem of the inverse function shows that g is locally invertible in the neighborhood of 1 and 1. If I try to make the substitutions of 1 and 1, you will end up having, this is 2, 2, 2, 2, and once you try to evaluate it, it's going to equal to 0. So this guy not correct, this guy is not correct, this is the correct one, as I told you. So once more, this is the correct answer, and this is because the test by itself, if it is C1, if it is finding the Jacobian, the determinant of the Jacobian of this function. This is also on the same example, 2 of x, y squared, and he is asking you to get the Jacobian of j minus 1 at 0 form. He wants you to get the Jacobian, the Jacobian matrix of g minus 1, of the inverse function of g. Okay, let's get the g function. But unfortunately, if you try to get the inverse function from here, from this transformation, this is not linear system of equations. It's going to be very difficult to get g minus 1. Then you will substitute by 0 form. But instead of this, I can use this relation, which means that the Jacobian of g at y equals the Jacobian of f at x, 1 over the Jacobian. So now I can use this relation, which one of the benefits of this function. So once more, I will, although I can't isolate it, I can't get the inverse function as clear as possible, but I can use this relation, that the Jacobian of g at the values of y, which is f of x and y, whatever in values, equal to 1 over the Jacobian of the, this is for g minus 1 of course, this is the Jacobian of the g at the values, but these are x1 and y1. So this is fx1, y1. And this is at x1 and y1 as I told you. So this is the inverse function that I'm telling you about. Once more, this is the inverse of g. The problem is I need to find x1, y1.